Hi, I'm Patrick Reagan. Welcome to the Advanced Networking Concepts, Part 11, Troubleshoot Common Performance Issues. During this video, we will dig deeper into various performance problems found in networking. Topics will include congestion, bottlenecking, latency, packet loss, and jitter. As always, stick around for the practice questions at the end to test your knowledge and help you prepare for the Network Plus exam. If you find this video helpful, don't forget to click the like button, and if you have not already, subscribe to the Pat Has Your Back channel for more tech training content and technical know-how. When dealing with your networks, you need to be concerned with network performance, metrics, and security vulnerabilities. Many technologies such as voice and video on an IP network relies heavily on stable, well-configured internet connection, and users just expect the network to work when needed. Bandwidth is the maximum theoretical capacity of a network link to transfer data. Bandwidth represents maximum potential, such as a 1 gigabits per second connection. Throughput represents the actual rate of transfer. For example, you're downloading at 500 megabits per second. In other words, while bandwidth is the potential speed, throughput is the real speed. Bandwidth is fixed by the infrastructure, while throughput is affected by network congestion, latency, signal quality, and device performance. Both are typically measured in bits per second. Actual throughput is almost always lower than the maximum bandwidth due to network congestion, packet loss, and latency. If you have a 100 megabit per second internet plan, which is your bandwidth, your download speed or throughput might only be 80 megabits per second due to high traffic in your area. The percentage of available bandwidth or utilization currently being used for a 1 gigabits per second link that is moving at 800 megabits per second is 80%. High utilization, greater than 85 to 90%, is often an early warning of a bottleneck. As I've already mentioned before, throughput is often lower because of network congestion, where too many users sharing the same highway slows everyone down, latency, which is the delay it takes for a packet to travel back and forth. High latency can throttle how fast data is sent, even if there's plenty of room. Packet loss. If data gets lost and needs to be resent, the overall amount of new data successfully delivered throughput drops. Protocol overhead. Every piece of data needs packaging, like an envelope, to know where to go. The packaging takes up space that could have been used for the data itself. Congestion, the traffic jam, occurs when data traffic exceeds network capacity, leading to latency, packet loss, and slow speeds similar to a traffic jam. Contention, the competition, is the competition among devices for shared resources such as bandwidth or airtime, which often causes congestion when demand is too high. While congestion is the state of being overwhelmed, contention is the underlying competitive cause for that state. Bottlenecking refers to the point of congestion where the flow of data is constricted, limited, or slowed, causing the entire system's throughput to be restricted to the capacity of that single slowest component. It's essentially an internet traffic jam where the volume of data requested exceeds the available bandwidth or processing capability of a network device, leading to increased latency, packet loss, and poor user experience. Network bottlenecks arise when the demand for data transmission exceeds available capacity, often stemming from hardware, software, or configuration issues, including insufficient bandwidth, whereas the total volume of traffic exceeds the maximum data transfer rate of the connection. Outdated or inadequate routers, switches, modems, or NICs may not support modern high-speed data transfer rates, creating a choke point. Too many devices on the same local area network or wireless network can compete for bandwidth, causing contention. Poor network configuration, including duplex mismatches, such as half duplex instead of full duplex, or incorrect maximum transmission unit sizes. Weak Wi-Fi signal or interference, often caused by physical obstructions, distance from access points, or interference from other devices operating on the same frequency, such as microwaves. Server device overload, including server resources, including CPU, RAM, or disk I/O, is overwhelmed, preventing it from sending or receiving data quickly, even if the network path itself is clear. Bandwidth hogs, where specific application users performing high-definition video conferencing, constant streaming, or downloading large files, can monopolize available capacity. And slow DNS resolution, where clients are waiting for name resolution. To mitigate bottlenecks, upgrade your infrastructure. Replace old hardware with modern, high-speed alternatives, such as upgrading from Cat5 to Cat6 cables and replacing legacy switches with gigabit switches. Implement quality of service or QoS, which prioritizes critical traffic like VoIP or video calls over non-essential traffic to manage congestion. Segment the network. Use VLANs to divide a large network into smaller, more manageable subnets, reducing broadcast traffic. Load balancing. Distribute traffic across multiple servers on network paths to prevent any single device from being overwhelmed. And monitor traffic, or use network monitoring tools to identify the specific source of congestion. To see your current network performance, use tools like Speed Test by Ookla or Fast.com by Netflix to see your real-time internet speeds. For local network performance, IT professionals use tools like iPerf to measure the maximum achievable throughput between two devices. For a comprehensive method of measuring performance for an organization, use the following. Network monitoring tools, where you deploy tools such as SolarWinds, Opkio, or Cisco Thousand Eyes for comprehensive visibility, traffic flow analysis, and automated alerting. Simple Network Management Protocol, or SNMP, which uses SNMP to query routers, switches, and firewalls to monitor device health, throughput, and error rates. Active monitoring, using synthetic testing, where you use tools that inject simulated traffic like ICMP pings to measure performance between specific points in real time. And flow-based analysis, such as using NetFlow or IPFix to understand who is using the bandwidth and for what applications. NetFlow, developed by Cisco Systems, is a network protocol that collects and monitors IP traffic flow data, providing detailed visibility into network usage, traffic patterns, and security, rather than full packet capture. It captures metadata, including source and destination IPs, ports, protocols, and byte and packet counts, which is sent to a collector for analysis. Internet Protocol Flow Information Export, or IPFix, is an IETF standardized protocol used in networking to collect, export, and analyze IP traffic flow data from routers, switches, and firewalls. Often called NetFlow version 10, it is a flexible, vendor-neutral protocol that provides deep visibility into network performance, traffic patterns, and security, aiding in troubleshooting and monitoring. When measuring and monitoring network performance, you should perform the following steps. Establish a baseline. Measure performance during normal, non-congested times to set a benchmark. Monitor consistently. Use automated monitoring to track changes 24/7. Set alerts where you configure thresholds for high latency or packet loss to proactively address issues. And simulate user experience. Test application performance from end user's perspective. Latency is the time delay for data to travel from source to destination, typically measured in milliseconds. It represents the lag in network communications affecting responsiveness. The round-trip time it takes for data to travel from a client to a server and back. It is caused by physical distance, network congestion, inadequate hardware, and large data payloads. Packet loss can cause latency as packets may need to be retransmitted. Latency can be further broken down by propagation or distance, serialization that occurs during data conversion, processing as the router determines where to send the data to, and queuing, which is where data is waiting in line to be sent or processed. To mitigate latency, utilize content delivery networks or CDNs to cache content closer to users to reduce physical distance. Use Ethernet instead of Wi-Fi for a more stable, faster connection. Reduce network congestion by limiting bandwidth-heavy activities such as large downloads and streaming. Optimize infrastructure by regularly update router firmware and replace outdated hardware. Optimize application by minimize file size and utilize edge computing. Lastly, use load balancers to distribute traffic and implement traffic shaping to prioritize critical data. Packet loss in network performance refers to the failure of one or more data packets to reach their intended destination across the computer network. It is measured as the percentage of lost data, causing reduced speed, high latency, jitter, and degraded performance in applications like VoIP, streaming, and gaming. Common causes include network congestion, hardware issues, faulty network drivers, and weak signal strength. Packet loss leads to dropped, slow, or inconsistent connections. As little as 2% packet loss can cause noticeable, severe service disruption. Under Transmission Control Protocol, or TCP, lost packets are retransmitted, which causes delays. Under User Datagram Protocol, or UDP, data is not recovered, leading to gaps in real-time data. Packet loss is often resolved by optimizing network infrastructure, reducing congestion, or upgrading hardware. Jitter is the measure of variability in the latency or delay of data packets arriving at their destination, typically measured in milliseconds. In other words, is consistency in the time it takes for data packets to travel across the network. High jitter causes inconsistent packet delivery, leading to poor quality in real-time applications like VoIP, video conferencing, and gaming, causing choppy audio, pixelated video, or lag in online games. Jitter is primarily caused by network congestion, improper queuing, or route changes. For voice and video, jitter should be ideally under 30 milliseconds, with some standards suggesting under 15 to 20 milliseconds for optimum performance. High jitter is often caused by insufficient bandwidth or unreliable connections such as Wi-Fi. It can be mitigated by use jitter buffers, which temporarily store packets to allow for smoother, albeit slightly more delayed playback. Enable quality of service, or QoS, so that routers can prioritize time-sensitive traffic like voice or video over background downloads. And use an Ethernet cable instead of Wi-Fi to eliminate environmental interference. Question: a geographical remote office needs to connect to the internet using a satellite WAN link. Which of the following is the two greatest concerns for this type of connection? Choose two answers. Answer: jitter and latency. Question: when a user makes a VoIP phone call and finishes speaking, the user experiences a delay in hearing a response. Which of the following should the network engineer check? Answer: latency. Question: several users in an organization report connectivity issues and lag during a video meeting. The network administrator performs a TCP dump and observes increased retransmissions for other non-video applications on the network. Which of the following symptoms describe the user's reported issues? Answer: packet loss. Question: while troubleshooting a network, a VoIP system engineer discovers a significant inconsistency in the amount of time required for data to reach its destination and return. Which of the following terms best describes this issue? Answer: jitter. Question: an ISP configured an internet connection to provide 20 megabits per second, but actual data rates are occurring at 10 megabits per second and causing a significant delay in data transmission. Which of the following specifications should the ISP check? Answer: throughput. Question: you're monitoring a fiber uplink to a remote office and notes the uplink has been operating at 100% capacity for a long duration. Which of the following performance metrics is most likely to be impacted with sustained link saturation? Answer: latency. For more information, refer to these sites. When dealing with networks, you need to be concerned with network performance metrics and security vulnerabilities. Many technologies, such as voice and video on an IP network, relies heavily on a stable, well-configured internet connection, and users just expect the network to work when needed. While bandwidth is the potential speed, throughput is the real speed. Congestion, the traffic jam, occurs when data traffic exceeds network capacity, leading to latency, packet loss, and slow speeds similar to a traffic jam. Contention, the competition, is a competition among devices for shared resources such as bandwidth or airtime, which often causes congestion when demand is too high. Bottlenecking refers to the point of congestion where the flow of data is constricted, limited, or slowed, causing the entire system's throughput to be restricted to the capacity of the single slowest component. Latency is the time delay for data to travel from source to destination, typically measured in milliseconds. Packet loss in network performance refers to the failure of one or more data packets to reach their intended destination across the computer network. Jitter is the measure of variability in the latency or delay of data packets arriving at the destination, typically measured in milliseconds. Thank you for watching this video. This completes advanced networking concepts. The next series of videos will be physical installation. Thank you.